So today we're going to be going over a few aspects of exponential form. Now, a big thing that we see confused in a lot of public literature is the difference between a growth factor and a growth rate. So a lot of what we're going to be going over today is just the difference between the terminology. Because if you're reading over something that's talking about a factor and you see that they're referring to a rate, that's very different than a rate versus a factor. If I have a rate of, let's say, 10%, I know that that's going to give me, if I have a rate of 10%, that means that my rate is actually 0.1. I'm going to take 1 plus that and say, okay, I'm increasing by a rate of 10%. So my B is actually 1 plus 0.1. So my B is 1.1. Again, with most values that are relatively low, it's pretty easy to tell the difference between the two, but again, it's just an important idea that we know the difference between factors and rates. So today what we're going to be going over is the growth factor. If I have a growth factor of 2, I know that my B is going to be equal to 2 of the equation y equals A times B to the power of x. My B is 2. That's all that I need to know. I have a growth factor of 2. Now, conversely, if I have a decay factor, what I know is that my graph is going downwards. So I'm not actually multiplying by 2, I'm dividing by 2. So I'm going to put 1 over 2. That tells me I'm dividing by that number. Now, if I have a fraction and I have a growth factor of 2/5, well, technically that would be a decay factor, but if I have a growth factor of 2/5, my B would be 2/5. I'm multiplying by 2/5 each time. So again, technically to have a growth factor, that upper number would need to be higher than 5 because that 2/5 is going to be shrinking. And conversely, if I have a decay factor of 2/5, again, a decay factor means that we are decreasing. We're going to actually be dividing by this. So my B would be 1 over that. So we're going to keep change flip, would be 5/2. So these are actually going to be the terminology. Let's go ahead and fix these. This would be a growth because my B is going to end up being larger than 1, and this would be a decay because, again, my B is less than 1. So a little bit of a terminology screw up there on my behalf. Likewise, if I have a percent increase or a percent decrease, I know my B is equal to 1 plus or minus R. Increase means I'm adding that rate. So my B is just 1 plus 0.02 or 1.02. Nothing too crazy. Likewise, at percent decrease, I'm going to do the exact same thing. My B is 1 plus or minus R. With decrease, I'm subtracting it. So 1 minus 0.18. So B is equal to 0.82 or 0.82. There we go. Now if I have a 112% increase, no different. 1 plus 1.12, that's 112 expressed as a decimal. So my B is 2.12. And if I have a 175% decrease, I know my B is equal to 1 minus 1.75. So my B is equal to negative 0.75. Again, we're going to run into some issues here because if I'm decreasing and I have a negative B, I know what's going to happen with the graph is going to do one of these oscillation things as it slowly zeroes in on a point. And typically we're not going to see behaviors continually decrease if every other time they increase. So again, a little bit of a terminology error here. We don't generally express percent decrease greater than 175% on a continued basis. It's just kind of a one-time shot. If I increase by a factor of 2, well, okay, that means my B is equal to 2. So there's my factor of 2. If I decrease by a factor of 9, well, that just means my B is 1/9. That's a different way of saying decay factor. Same thing if I increase by a factor of 1/3. Well, again, So what we're seeing here is this is where a lot of the ambiguous wording comes into play. We're increasing by a factor of 1/3, which means my factor of 1/3 should be my b, which would make me question, is this actually a decrease? Or if I'm increasing by a factor of 1/3, does that mean that I'm increasing by 1 and an additional 1/3? Would that mean that I'm actually dealing with a rate? And again, a lot of common literature or a lot of public literature where people use terminology like this, it's rather ambiguous and a little confusing because my b could be 1 plus 1/3. So that way I'm getting a number larger than 1 so that I am increasing, because this would signify a decrease. But then again, that would not be a factor of 1/3. That would be a rate of 33%. So again, we're not really sure what's going on with this one. Same thing with this. If I'm decreasing by a factor of 1/3, well, that could mean that my b is just 1/3. But again, if I'm decreasing, typically we look at that as b equals the flip of 3/1. That would be a decay factor. But again, that is going up. And lastly, I could say, am I decreasing by a factor of b could be 1 minus 1/3. So I'm decreasing by a factor, which would mean that would be technically a rate. So again, we're not really sure what's going on if we end up with wording like this. We tend to want to stick to, we have either growth or decay by a factor of 2 or a factor of 4, something very straightforward like this. When we start getting into fractions, kind of ignore the terminology. The factor is 2/5, the factor is 2/5, or if we're going up, the factor is 5/2. Percent increase, we typically want to keep those values below 100% because when we start going above 100%, we get with some sort of ambiguous terms. So again, this is one of the big reasons why we go over this terminology so that we can understand what exactly is being said and where we might run into problems if the literature isn't using terms that are properly expressed. So let's take a look at a few examples of said terminology. So with this, we're looking at the population of Greenville. It's got 8,000 people, and it grows by 5.6% each year. Write a function for the scenario. So what we're going to be doing is we're going to be using the formula y equals a times b to the power of x. I know I'm increasing by a rate of 5.6%, so I know I'm not using my factor. I'm going to say y is equal to the starting value of 8,000 times 1 plus 0.056 each year. And so because I want to write this in function notation, I'm going to say, hey, the population is a function of the number of years. So it's 8,000 times 1.056 raised to the yth power, because y is my variable. And so the first few questions are just simply asking, okay, what's the population after 10 years? So we're going to take our equation and say, well, that's going to be piece of 10 is 8,000 times 1.056 raised to the 10th. Now, what we could do is we could say that is 1.056 raised to the 10th power. Write that down and then multiply it by 8,000. What we're going to do is we're not even going to clear the calculator to keep as many decimals as the calculator stores in its memory, and just multiply times 8. So now my population after 10 years has increased to 13,795.2. Then you're going to ask yourself, can I have 0.2 people? No, this one hasn't quite gotten done being born. So it's 13,795 people. Likewise, the same setup over here. It's just going to be a piece of 15. Figure out what the population is after 15 years. So we get 1.056 raised to the power of 15. We get that, but without clearing it, I'm going to go ahead and multiply it times 8,000. So that way I don't have any rounding errors. So I know that my population as a function of 15 years is 18,115.4. But again, that person hasn't been born yet, so it's 18,115 people. One of the big things you want to get in the habit of is making sure you don't actually write out an abbreviated decimal. What many people do is they put 1.056 raised to the 15th power, and they say, that's 2.26. And they'll take 2.26 and multiply it times 8,000. And we'll notice that here, I'm off by a factor of 115 from 80. That's 35 people. So if you're looking at it, it's just a set of numbers, not a big deal. But if we're looking at it as a set of how many people did you predict, well, that's a lot of people that may end up going hungry due to a rounding error. So we want to make sure we don't clear fractions or clear decimals if we have the ability not to. The same concept applies with money. Now again, the wording in this question might be improved a little bit because simple interest, what that would mean is that I would take $700 and I would figure out what 0.02% is of that $700, which would be 7 times 0.02, 700 times 0.02. Now again, that's $14 a month would be the increase, regardless of how much money you have in savings. So what we really should say here is 2% interest compounded each month. That's going to allow us to say, okay, after the first month, that extra 14 bucks is also earning interest. And that's going to turn this from well, it's just a simple addition to something that's going to be an exponential form. So here I'm going to say we have $700 and I increase at a rate of 0.02, so my 2%, raised to the x power. If I want to turn that into a function, let's say my money, we're going to use an m for that. My money is a function of the number, money is a horrible letter. We're going to say our dollars. So our dollars is a function of the number of months because it's each month. So I don't want an m of m. We're going to say dollars is a function of months. 700 times 1.02 raised to the number of months. Perfect. So we have this. So we're going to ask, how much will the account hold in 2 years? Well, what you might be tempted to do is put a function of 2. But again, let's think about years, months. Let's see, there's 2 years, 12 months in a year. That's going to be a function of 24 months. So I'm going to take 1.02, raise the 24th without clearing it, multiply it by 700. That means after 24 months, we have over $1,000 in our bank account. 96. So this number right here, you haven't quite earned that penny yet, so the bank's not actually going to pay you. They're going to say you've earned $1,125.90 in 24 months. If you leave it in a little longer, we'll give you that extra penny. But if we look at this as a factor of 10 years, well, that's going to be 120 months. So 700 times 1.02 raised to the 120th. So 1.02 raised to the 120th power. Cool, so we're multiplying that 700 times roughly 11. So you have over $7,000. Again, you haven't earned that last penny. So you have $7,535.61. Well, and there we go.